Hello, and welcome to my presentation for the SURE 2010 research program. My work concerns the modeling of syngas combustion, with the goal of resolving a notable discrepancy between current numerical models and experimental data. I'm advised by aerospace engineering professor Matthias Ime. Synthesis gas, or syngas, is an emerging alternative fuel. Produced from many hydrocarbon-rich sources, its exact composition varies, but most blends are composed primarily of molecular hydrogen and carbon monoxide. Minor components include carbon dioxide and methane. Syngas has particular potential in the field of stationary power generation, where it is competitive on an efficiency basis with fossil fuels, but offers significantly reduced emissions. Integrated gasification combined cycle systems are one example used to generate electricity from coal-derived syngas. Rapid compression machines, or RCMs, are commonly used in experimental combustion studies. Though similar in concept to the piston cylinder assembly of a reciprocating engine, the RCM has several unique features. Most consist of a single cylinder divided by a free piston. On one side, a fuel-air mixture is loaded, and the other side is filled with compressed gas, usually air. When the piston is released, this pressure difference moves the piston, and the fuel-air mixture is compressed, raising its temperature and pressure as a result. Once the piston reaches a predetermined position, it locks in that position for the remainder of the experiment. After a certain time period, the mixture ignites, and this time period is the focus of my research. To simulate the operation of an RCM, I am using the Cantera software package, created by Professor David Goodwin of the California Institute of Technology. My simulations model the operation of the rapid compression machine in the University of Michigan Combustion and Synthesis Kinetics and Diagnostics Laboratory, directed by Aerospace and Mechanical Engineering Professor M.S. Wooldridge. One of the more important pieces of data that can be obtained from RCM studies is ignition delay time, which, as the name implies, is the time taken for the fuel-air mixture to ignite after compression is completed. Since ignition delay time is a general characteristic of a fuel, it is important not only for proper combustor design, but also validation of numerical models. A recent study showed that current numerical models overpredict ignition delay time by up to several orders of magnitude in comparison to experimental results under conditions applicable to power generation turbines. My work addresses this discrepancy by attempting to identify a phenomenon not included in current numerical models which may resolve it. Experimental results have shown that combustion of a fuel-air mixture initiates at discrete locations, or kernels. These kernels then transfer heat and radicals to the surrounding mixture, facilitating combustion of the mixture as a whole. Most contemporary models are zero-dimensional and thus cannot capture this phenomenon. My model allows ignition kernels to influence the rest of the mixture via interaction by exchange with the mean effects, or IEM, which is governed by volume average mass fraction and specific internal energy values, as well as a characteristic time. To account for heat transfer through the walls of an RCM, my model divides the fuel-air mixture into two zones, separated by the edge of a thermal boundary layer. The region near the walls includes the majority of viscous effects, while the region in the core of the cylinder is approximated as adiabatic. A discrete number of gas cells are modeled in each zone, and each may begin the simulation with a temperature different than the mean temperature of the mixture as a whole. Additionally, mixing effects via IEM are governed by the value of a characteristic time. Gas cell interaction is modeled via turbulent mixing, which is addressed with the K-epsilon closure model. This provides the characteristic time as a function of the current time, a characteristic mixing length, an initial perturbation velocity, and several constants. It is clear from the IEM model described that an increased perturbation velocity will lead to greater mixing between cells. The question then arises of whether variations in this parameter can cause orders of magnitude reductions in ignition delay time. This arrives at the focus of my research, whether experimental considerations such as turbulent mixing and a non-uniform initial temperature profile can explain the current discrepancies in ignition delay time. This work was supported by a grant under the Summer Undergraduate Research and Engineering Program by the University of Michigan College of Engineering. For details, please visit the college website. Thank you very much for your interest in my work, and go blue.